In the last lecture, we talked about the natural numbers, the numbers 1, 2, 3, 4, 5, and so on forever. And last time we were talking about the natural numbers as they are used for the purpose they were invented, namely counting things. And we saw how they applied to counting numbers of people and numbers of money and all sorts of things. But for thousands of years, people have been curious about numbers for their own sake. And in fact, one of the strategies of thinking that mathematics is really a paragon of is the strategy of abstracting from an idea and then dealing with that abstract idea and investigating it for its own sake. And the natural numbers have been a collection of ideas that have inspired the imagination of people from cultures around the world and throughout time. At least for thousands of years, people have been investigating numbers for their own sake. So in this lecture, we're going to talk about one of the questions that stumped mathematicians for hundreds of years and really ties us back to ancient Babylonian times up to the modern day. So I thought you'd enjoy hearing a little bit about Fermat's last theorem. This story starts in 1637 in France, when Pierre de Fermat was sitting reading a book, an ancient Greek mathematician's book called Arithmetica. It was a book by Diophantus, and it was about numbers, talking about the relationships of numbers. And as Fermat read this book, he looked at this book, and the book was talking about Pythagorean triples, which I'll tell you about in a little while. But he was reading this book, and he was taking notes, and in the margin of the book, he wrote the following little inscription that inspired tens of thousands of hours of work by mathematicians for the next 350 years. And this is what he wrote. He said, "It is impossible to write a cube as a sum of two cubes, a fourth power as the sum of two fourth powers, and in general, any power beyond the second as the sum of two similar powers. For this I have discovered a truly wondrous proof, but the margin is too small to contain it." He wrote those words, that the margin is too small to contain a proof of this statement, and then 350 years passed without its being solved. So this is the statement as it would appear in modern day notation. So here we see Fermat's last theorem. It would be expressed now by saying that you cannot find numbers x, y, and z, whole numbers, x, y, and z, regular numbers, so that x, when raised to the n power, that is x times x times x n times, plus y to the n power equals z to the n power. You cannot find non-zero numbers x, y, and z that satisfy that relationship except for the exponent 2. You see, in this book that Fermat was reading, probably he was reading the section about Pythagorean triples. Those are numbers such as 3, 4, and 5. You see, 3, 4, and 5 have the property that 3 squared is 9, plus 4 squared, that's 16, equals 25, which equals 5 squared. So you see, Fermat's last theorem says that you cannot find a collection of three numbers like that if the exponent is bigger than 2. But we see that for the number 2, there is such a number, and in fact we'll see that there are infinitely many numbers. So in 1637, Fermat posed this question. And it turns out that he was probably wrong in his assertion that he had a wondrous proof. He, by the way, didn't die until many years after writing this, so presumably if he had had a proof, he would have made it known to somebody. But he did prove related things, and we'll talk about some of those that he did prove. But he wasn't able to prove his whole conjecture. But 357 years after he posed this question, in 1994, a gentleman by the name of Andrew Wiles, who's living today, proved that, in fact, Fermat was correct. But we know for sure that Fermat did not have in mind the proof that Andrew Wiles constructed, because Andrew Wiles' proof is an enormously complicated thing. So that, and it involves mathematics that was developed in the next 350 years since Fermat's time, ideas that Fermat never had and that no one in his era had ever thought of. Mathematics is a developing subject. It's not all there and wasn't there in the 17th century and is not there now. Things are being developed and discovered all the time. Whole ideas are being developed. And to attack this problem of Fermat's last theorem, it uses areas of geometry and other areas of mathematics that seem unrelated to a question about integers. So Andrew Wiles proved this theorem in 1994 after building on the work of many others. If Fermat had had that proof in mind, instead of writing this margin is not large enough to contain it, probably Fermat would have written a large truck would not be large enough to contain the proof because it would take all these thousands of pages of mathematics in the intervening years. So Fermat's theorem is really what it first of all has, in a sense, no practical application. Nobody is going to build a bridge using the fact that this is always true or not true. And in fact, at the time that it was proved, that is, that there were no integers x, y, and z, so that x to the n plus y to the n equals z to the n, it was known to be true for all exponents up to hundreds of thousands. So it was for all practical purposes. There was no sense in which people were eagerly hanging on this question. But on the other hand, the fact that it was unresolved for all these years made it a real prize for mathematicians for over the many, many centuries. And I think it also offers all of us a philosophical inspiration. Namely, here's an example of a problem that stumped all of humanity, and the best minds of the world were thinking about it for hundreds of years, and now it's solved. Difficult, but it's solved. So maybe it gives us some hope that problems of other sorts that have been unsolved for centuries or millennia can be solved. So I think it has an inspirational value as well as a mathematical value. But I wanted to tie this Fermat's last theorem back even further than the 17th century and go all the way back to ancient Babylonia. There's a Babylonian tablet that was written in the years 1600 BCE or 1800, somewhere in that era. So we're talking almost 4,000 years ago. And on these tablets, there appear pairs of numbers. But actually, these pairs of numbers are 2/3 of triples of numbers. The triples of numbers are numbers with the property, like 3, 4, and 5, that 1 squared plus another 1 squared equals the third 1 squared. So in ancient Babylonian times, and here you can see these examples that are numbers even into the thousands, where if you raise them to powers, you indeed see this relationship. Well, when you see something like this, you know that the ancient Babylonians didn't have computers, for example. They couldn't do computer searches and take 5-digit numbers and square them in order to find these numbers. Probably there was some method that they used to find these numbers. But people don't really know whether they had a method, but it is known that in ancient Greek times, there were methods known to create these so-called Pythagorean triples. And so what we're going to do now is talk about how it is, if you wanted to create 3 numbers so that the square of the first plus the square of the second equals the square of the third, how could you do that? And I will show you how to construct infinitely many. As many as you want, you can just construct them all you want. And the neat thing about these, of course, the association you have with these numbers, like 3 squared plus 4 squared equals 5 squared, is that you can build a right triangle because of the Pythagorean theorem. You know that the square of this side plus the square of this side is equal to the square of this side. So you could build a right triangle that has integer length sides that was a perfect right triangle. And in fact, carpenters can use that to make a right triangle. You take something 3 long and 4 long and 5 long and stretch it out and you'll make a perfect right triangle. So the Pythagorean triples can be generated by the following method. So here I'm going to show you how to do this. You're seeking 3 numbers. that have this property of the first squared plus the second squared is the third squared. And in order to do that, you use two auxiliary numbers to create those three numbers. So what we'll do is just take two numbers and we'll call them s and t. And if you take any integer s, any one you want, and any integer t, any other one you want, as long as they don't have any common factors, then here's what you can do. You can take those two numbers and create three numbers. One, 2 times the product of those two numbers. The other, the square of the first plus minus the square of the second. And the third one, the square of the first plus the square of the second. And you'll create three numbers. And those three numbers will satisfy the condition that the first one squared plus the second one squared equals the third one squared. Now, there's just a little bit of algebra. Don't worry about it if you don't like the algebra, but it's very simple to see. So the algebra is here on your screen. You can just see that if you take two numbers s and t, any two numbers s and t, if you take 2st and you square it, and you add it to s squared minus t squared all squared, that when you expand that square, s squared minus t squared becomes s to the fourth minus 2s squared t squared plus t to the fourth. When you add to that the 4s squared t squared, which was 2st squared, you can see that what you get is the expansion of s squared plus t squared squared. So just this simple algebra shows you that if you take any two numbers s and t, you can create this neat Pythagorean triple, or a right triangle that had these properties. Let's just do it for some simple ones and you'll see. Suppose you take s equals 1 and s equals 2 and t equals 1. And let's just do the arithmetic. So 2, that's s, squared, minus 1, that's t, squared, equals 3. 2 times the product of s and t, 2 times 2 times 1 is 4. And then the final number is going to be the square of the first, that's 2 squared, plus 1 squared, that's 4 plus 1 is 5. And sure enough, we see that it's true that the first number generated, 3 squared plus 4 squared, is equal to 5 squared. Let's do another one just for fun. So you see, you can just pick any two numbers you want. So this is something you can do in the privacy of your own home, you see. You can do it, you pick any two numbers, put them in there, and you get these Pythagorean triples. And you could actually build triangles that have integer sides just by doing this. So let's try another one. So s equals 3 and t equals 2. If we just do the arithmetic once again, 3 squared minus 2 squared, that's 9 minus 4 is 5. 2 times 3 times 2 is 12. And 3 squared, that's 9, plus 2 squared, it's 4 more, is a total of 13. And indeed, 5 squared plus 12 squared is equal to 13 squared. So those are familiar ones. Let's try one that's probably less familiar to you. We'll take two numbers at random, s equals 7, t equals 4. And just doing the arithmetic again, taking the difference of their squares, we get 33. Their product times 2, we get 56. And the sum of their squares is 65. And indeed, if you take out your calculator and you take 33, you square it, take 56, you square it, it equals 65 squared. So I think these are sort of amazing that you can create these triples by themselves. Well, let's think about the Pythagorean triples, and particularly those big ones. You see, now maybe the Pythagoreans had a method, and by the way, there are different methods for creating all these numbers, although this is the method that creates all of them. But there are some other methods that will just create some of the Pythagorean triples. But just for fun, let's just note that if you choose s to be 125 and t to be 54, that those are the two numbers that create the Babylonians' Pythagorean triples that occurred on that clay tablet, the biggest ones that occurred on that clay tablet. And in fact, every one of the triples that appeared on that Babylonian tablet and every other triple can be created by choosing an s and a t appropriately. So I don't want people to feel that mathematics is a magical thing. When you see relationships like this, choosing s and t, and you square one and square the other, and you add them together, I mean, sometimes people think that mathematics just comes out of nowhere, or that some great genius just happened to think of it and lives in a different world. But that's really not the case. What actually happens, and the way mathematics is developed, is that people just have clear insight that is pushed forward in a logical reasoning way, and that you get the insight by following logical consequences of good ideas. So let's